are pretty similar. When we did percent change, if you remember, the process was percent change is equal to your new value minus your original divided by your original, and we multiplied that by 100% to turn it into a percent. Okay. We then did percent error. Okay. And we said that was your estimated value, since we use E for estimated value, or it could have been measured value, minus the actual value, which the actual value is actually something that is usually found maybe through scientific facts or maybe manufacturing. We know what a certain distance is in actuality. So that there's going to be several different ways in how we determine the actual value, but we will be provided that, and we multiply that by 100%. Okay, there was the added feature yesterday that we put absolute value around that numerator. Okay, but it just tells us that percent error, you always view it as a positive number, even if you get a negative back. The error is telling you how far off of the actual answer you are, okay, or the correct answer or the correct value, and it doesn't matter to us whether we err on the larger side of the actual answer or if we err on the smaller side of the actual answer. We just care that we error from the actual answer. Does that make sense? So that's why I always view it as a positive number. If you want to put those absolute value bars in there, that's kind of the way it's formally done. But I'm just going to remind myself that it's always going to be positive. Okay, so here's kind of my hope that we recognize. If I look at these formulas, would you agree that the structure of these formulas is very similar? Okay, new minus original divided by original is very similar to the estimated minus the actual divided by the actual. They're the same formula. Okay, it's just the words that we use to describe those components are a little bit different. But you should be able to, in each one, if they say percent change, if they say what's the percent increase or percent decrease or percent change, they will give you a new amount. Okay, they'll tell you, okay, this is the amount after an increase or after a decrease or something like that, and they'll give you the original amount. And usually they'll say, this is the price, or this was the price, or this is the original price. So you can tell what's the original, what's the new. In the percent error one, they will tell you somehow that you did a measurement or you did an estimation, and that's what's going to be going in that green spot. And then they'll tell you, through some fact, we know that the actual measurement should be this, and that's what would go in the yellow. Okay, so if you can pull that stuff out of these questions, percent change and percent error should not be something that is excessively difficult. Okay, so this first example says an air turbine decreases its rotational speed from 5 rotations per minute to 3 rotations per minute. Calculate the percent decrease. Okay, so they tell me percent decrease. So I think it's a good idea, guys, to always write your formula down, especially when these formulas are a little bit new to us. If I write it down, I think I told you this maybe at the beginning of the year, it's like 6 times more effective to write something down in regards to memory than it is to hear it. So if I only hear this thing 3 or 4 times, but I write it down 4 times, that's like hearing it 24 times. Okay? So we want to be able to do that. Yes? Yeah. So we want to be able to write that formula. So now we look at that and I ask myself, okay, as I read this, do I know what the new value is? Okay, so what is the newer value up there when they talk about this rotations per minute? 5. 3. Okay, so because that's what we decreased from 5 to 3, so 3 is the new one. So we go 3. If 3 is the new one, then 5 was the original, right? So 3 minus 5, and I divide by 5. I'm multiplying that by 100%. Okay, so 3 minus 5 is -2, right? What's 2 divided by 5? 2/5, which is 0.4. Good. Okay, so it's 0.4. So move my decimal 2 spots to the right. When I multiply by 100, it would give me 40%, right? Now it would be negative. You remember yesterday when we got an answer that was negative, we then took the negative away and added the word decrease. So 40% decrease. Is that right? A lot of these things are like questions, or this process gives you the ability, maybe when you are older and you have to, pay an electric bill, and you have to pay a water bill, and you have to pay kind of those utility bills, you can kind of determine, what do I need to pay? If my electricity bill was $350 this month, and I need to get that down to $200, we can talk about maybe the percent decrease of the electricity that you need to consume would be. Does that make sense? So that's kind of the purpose of us kind of learning this. So as we become consumers later on and have bills and stuff like that, we can do a little bit of algebra to help us plan on how to be efficient with our money. Example 3 says Becky dropped a ball off a balcony and calculated that it would take 2.0 seconds to hit the ground. Okay? It says in actuality the ball took 2.12 seconds to hit the ground. Find the percent error in her time. Before we do this, you guys watch the Olympics? I don't think we even have them. I think we have these here when we run a track meet here. In a track meet, so let's say that here's my finish line. So I try and give you kind of almost a 3D kind of image. And my track would be between them, right? So here's my finish line. Okay, there is a laser that goes between those two posts on my finish line. Does that make sense? So instead of having somebody standing there with a tape or a stopwatch, okay, this thing is linked over to the side to a computer, okay, and when somebody breaks that beam of that laser, kind of like on your garage door, when it breaks that beam, it's going to send a signal to this computer to calculate the time. Does that make sense? Okay, and that is going to be extremely accurate. Okay, almost exact. Okay, much better than somebody with a stopwatch sitting there and just clicking the stopwatch every time somebody finishes. Does that make sense to everybody? Okay, so the same idea then happens with this kind of ball. How do they know the ball took actually 2.12 seconds? So what we've got here is she's going to drop this ball off of this height, okay? We can assume that then down here at the bottom, there's kind of a laser down here, and when that ball breaks that laser, it's going to stop the time. Does that make sense? Okay? When I was in school, we see these questions, and I'm thinking, yeah, I can do this stuff, but how do I even know where do I get that 2.12? There are scientific ways for us to get that, right? And those devices are not all that rare or expensive to actually have. Okay, so that's where that 2.12 is coming from. I just want to make sure we understand that that's not just pulled out of thin air and we can't really find it. We can find it. Okay, so they're asking for percent error here. So percent error. Okay, if you remember the formula, it was estimated minus actual divided by actual. Then change it to a percent. So what do we estimate? Or remember, estimate or our particular measurement that we did. We measured it, right? So she said Becky dropped the ball off the balcony and calculated that would take 2.0 seconds. So the idea is that she knew that when she dropped the ball, she'd hit the stopwatch. And then she knew that when it was going to hit the ground, she was going to hit the stopwatch again, right? She's going to stop it. Well, if it's 2.0 seconds, so really what happened, she stopped it a little bit short, right? She stopped it before it hit the ground. Okay? And that's there's going to be human error in a lot of these things when we use stopwatches like this. So, this is 2.0 is my estimated or measured value. The actual value we know is 2.12. 2.12. We'll divide that then by the actual of 2.12. Okay? I'll then multiply that by 100%. And when we figure that out, you guys get 5.66% error. Okay? 5.66% error. What percent error allows us to do, guys, is just basically say, how close were we to the actual answer as a percentage? Okay? So when I say, 2.0 and 2.12, okay, they're close to one another, but how close are they? That 5.66 gives me a better idea of how to kind of compare their closeness. We would like in scientific experiments and just in general, error to be minimized, right? We would like that 5.66 to even be smaller if possible, okay? And we'll do an example here in a moment, kind of expresses that idea of how small we want the errors to be. When we get into other classes, so I'm trying to tell you that error and percent change will be things that we use elsewhere in other math classes, other science classes. They will tell you maybe in this science experiment, we are going to be okay with a 2% error. You are allowed to have a 2% error. And if I know my 2% error, then I can work my way backwards and kind of determine then, well, how much off can I be in my calculations? Does that make sense? If I'm allowed 2% error, maybe going back to like the graduated cylinder type thing, maybe I need a cylinder that goes down to like the milliliter, okay, instead of one that's at like ounces. Does that make sense? Okay, or if I'm on a rule, talking about the ruler yesterday, if I have a distance that I'm okay with a 2% error, maybe that means I need a ruler that has 1/16 of an inch marked on it instead of maybe 1/8 of an inch. Okay, so it just tells me we can work our way backwards to find and determine what instrument we need, the precision of the instrument that we need to conduct the experiment. The next one, do the next two on your own. Do 4 and 6 here on your own. Error is the estimated value or the measured value minus the actual divided by the actual times 100%. So what was your estimated value? 400. Actual value? 450. Multiply that out by 100. What'd you end up with? 11.11%, right? Okay. Okay. Next one. It says the price of a $10,000 ancient Ming Dynasty Chinese urn saw a price of 12%. What's the new price? Yeah. So if we're doing price increases, okay, we know, so this is a little bit different than the questions we've been asking, but we can still work the same logic. The questions we've been asking were, what were the percent increase? What was the percent change? Now what they're asking you for is what is the overall price. And there's kind of a couple different ways you can do this. We could actually set a formula up here using this information. Think about this. Could we go percent, think about this, percent increase, so that's a percent change, is equal to new minus original divided by original, right? Could I say percent change, which they say is 12%, is equal to, now my new value, I don't know that, that's what I'm looking for, does that make sense? Minus the original, what's the original value of this thing? 10,000. Does that set up an equation that I'm going to be able to solve? Does that make sense? You multiply both sides by 10,000. I wouldn't do it this way, guys. I'm just showing you an option. But I'd multiply both sides by 10,000. So 0.12 times 10,000 gives me, all I've got to do is move the decimal place, 1, 2, 3, 4 spots. So it'd be 1,200 equals now n minus 10,000 again. So now what do I do to solve for n?
Minus it.
Add 10, this is minus right now. Add the 10,000 to both sides. If we add 10,000 to both sides, that gives me my new price of this earn, right? Okay, that works. That's the answer. I don't think most people are going to approach it that way, okay? Because I think it's easier to do this. Now, this is my opinion. It's up to you, okay? But if I know it currently costs $10,000, okay? And this is the idea we talked about, like making or having a receipt at a restaurant and then paying with a tip, right? If my receipt comes out to $30, but I'm going to pay maybe a 20% tip, I pay all of that $30 plus 20% of that $30, right? Does that make sense? So here, if I want to buy this earn after the 12% increase, I know I'm going to pay 100% of that $10,000. But on top of that, I'm going to pay another 12% of that $10,000. Does that make sense? Well, the way I find 12% of $10,000 is I multiply that $10,000 by 0.12. Does that make sense, everybody? And that will tell me the monetary amount in regards to the increase. If I take 10,000 times 0.12, I get 1,200. That tells me how much this thing has increased. Well, if I buy it, I got to pay that 1,200 now, but I also pay the original 10,000 that it was. So if I add those two numbers together, do I get 11,200 again? Okay. This is the logic here. I'm going to, let's see here. Let's do this. Would you guys agree that what I have there written in red is the same thing that says 10,000 there? Is that the same thing as 10,000 times 1 plus 0.12? If I would distribute that 10,000 to this 1 and this plus 0.12, would it give me that and that? Does that make sense, everybody? Using distributed property. Can you add those two numbers together right now? Doesn't that give me 10,000 times 1.12? Does that make sense? Okay. If I multiply those together, it gives me that amount, which is my cost of my earn. Okay. But think about what that 1.12 is as a percent. If you change that to a percent, isn't it 112%? Does that make sense, everybody? So when you do a price increase, okay, you can you want to figure out what the new cost is. All you do is add that percent to 100 and multiply your original cost by that new percent. It's going to be greater than 100, and you're good to go. I think that's easier than kind of solving that formula. So if I said I have, if I say I have an increase of 30%, what would you multiply that 10,000 by? You'd multiply by 0.3 and then add that to the 10,000, right? So wouldn't it just be quicker to multiply by 1.3? Because I'm going to pay 130% of that original cost. If it's a 50% increase, that's 150% that I'm going to be paying for this thing. Okay? Does that kind of make sense to everybody? I don't care how you do it. Obviously, it's up to you. But my thought is I just hate doing this. I hate saying, okay, if I've got, let's say, a $150 pair of shoes, and I know they've been either increased or decreased, it doesn't really matter. Let's say increased by 10%. I hate taking this, multiplying this by 10%, which would end up giving me $15. and then I hate taking that $15 and adding it back in to the 150 to get how much I'm actually paying. Does that make sense? I would much rather take the $150 and multiply it now by 110%. Figure out that's going to automatically give me 165. Does that make sense? So it's up to you. If you want to do these two steps, by all means do it. Okay. We talked about it yesterday as if I've got $100 pair of shoes. Okay. And I'm going to have a 30% discount. So I multiply it by 0.3. That's going to give me $30, right? And I want to know how much do I pay for my shoes. Well, now I've got to take 100 minus 30, and I'm going to pay $70 for my shoes, right? Well, if I have a 30% discount, isn't that the same logic that says that I'm going to, instead of paying 100% of my original price, I'm only going to pay 70% of my original price? Does that make sense? What's 70% of 100? $70 right away. Now I just do that one calculation much quicker to get my overall price. Does that make sense, everyone? Again, if you want to go back, and I think you guys are, I don't know, misled. I don't know if that's a good word for it, misled at younger ages when you did this before, because you're always taught, like when I do sales tax, to multiply by the tax, by the percent, and get that total, and then add that to the original value. And now you get your total amount that you have to pay. You don't need to do it that way. Okay? I don't know if it's because when you were taught at that age, maybe we didn't understand the distributive property, or maybe the teacher that taught it didn't understand the distributive property. But I think there are techniques that can kind of expedite that process if you want to learn that. Okay, this next one. I want to kind of erase some of this stuff because it doesn't really matter what formula we use this in. I don't need that either. So it just says an often used approximation for pi is 3.14. Do you guys agree with that? Okay. Says use a calculator to find the percent error and using 3.14 instead of the exact value of pi when calculating the area of a circle. I want to do this a couple different ways. I want to open this program real quick to Huh? Well, then you're going to miss something. Why don't you just stand up and move to another seat? Get some blood flowing. If you go get a drink, you're going to miss. That'd be just like being asleep, wouldn't it? We're almost done.
What? You are?
Yeah.
Like almost done.
Yes.
Like after this, you can do whatever?
No. You can do whatever anytime you want to do.
No.
Anything. All right, so we've talked about in like middle school when you're trying to find the area of something or the circumference, you're allowed to use 3.14. In the directions they would say use 3.14. But is that really pi? No. Okay. So if that's not really pi, then how does that impact our answers? Okay. If we want the percent, what we're trying to find here is the percent error, and this would be the percent error that is seen in every calculation that incorporates 3.14 instead of pi. 3.14, okay, percent error, remember, is an estimated. Another word for estimated is approximated, right? Okay. Minus the actual divided by the actual, and we'll multiply that by 100%. So when I'm writing this one out, it says if you're going to use 3.14, that is your estimated or approximated value, minus the actual value. Now, I can't physically write out the actual value of pi, but I can use that symbol right there. Okay? Because our calculator will actually use that, right?
Yep, sir.
Okay? And then I will divide that by pi. And then we'll multiply by 100%. Okay? So, here's the idea. If I take, we'll just do this real quick here. Obviously, if I compare, wrong one, new worksheet mode. There we go. if I take pi and let's evaluate it out to, 20 decimals, okay? It should look like, I gotta do it this way. It's capital P for this program. So that's out to 20 decimals, right? Okay. If I just look at 3.14, so if I take that number and subtract 3.14 from it, so x minus 3.14, how can I do that? Oh, it's equals x minus 3.14. No? Let's go, so pi minus 3.14. There we go. So if I look at these two numbers, I kind of show you what I just did here. This is the difference between pi, okay, with absolutely no rounding, and the 3.14. So when I use 3.14 inside other formulas instead of pi, that number does not show up anymore, right? That number, that part of pi does not get used. Well, what we're going to do here is see, okay, well, then how much does that impact our overall answer? Okay? And this is going to be working essentially with maybe dealing with like the area formula for a circle. Okay? So when I do this percent error, we can go 3.14, that's my estimated value, minus the actual value of pi. And if I divide that by divide that by pi, then it gives me that number right there. Okay. Now, what that negative, you guys know what that 10 to the negative 4 means?
Yeah.
What's it mean? Okay, so what's it mean?
That you have to move the decimal place over 4 times.
Okay, so I move my decimal 4 spots to the left, right? And that's really where the decimal should be. Now, when I multiply this by 100, decimals will actually get out of that scientific notation, but it gives me that number right there. That number is a percentage right now, so it's 0.05%. If I look at the, we just make absolute value here. It's a 0.5%, basically. Does that make sense? No, it's not even half. Sorry, not 0.5%. It's 0.5%. So if I were to like kind of compare pennies to percentages, okay? So you'd have 100 pennies in $1, right? That 0.05 is taking a penny and cutting it into, like if this was a 5, this would be cutting that penny into half. Does that make sense? Okay. So this would be cutting it even further. Okay. So that's the idea. That's a very small amount. Does that make sense? Okay. But it still throws off our answers for area by quite a bit later on. It gets compounded. That error becomes greater and greater. Okay. So as you guys work through maybe other courses, maybe they said to, instead of using 3.14, they'd say evaluate or use, does anybody know a fraction other than 3.14 that they've seen? Have you guys ever seen 22 over 7? Okay. So let's say I put that out to 20 decimal places. Okay. And I don't know how many decimal places I need to go before this terminates or starts repeating. So you can see here that this is a decimal that repeats, right? So 142,857 right there. You start to see after that it starts repeating again, right? So because of that repetition, we find out that this number 22/7 is very close to pi. If we look at pi up there, 3.14159. Okay, so we're really accurate out to, again, maybe, so this is where this decimal place here compared to this decimal place here is where we change. Okay, so, but I want to show you that that number as 22/7. So let's just put, instead of 3.14, let's put 22/7 here. And I want to have both of them here. I want to see the comparison. So let's cut and paste that. Do you see how using 22/7 drops this error? So 22/7 is a better number to use. It's closer to pi than what 3.14 is. Is that okay with everybody? Okay. A couple others that work a little bit better than that would be 333 over 106. Okay, you see that drops it even further, right? Okay. The better this approximation is, the less and less error we have, right? So here's the idea. This number, as I'm increasing 3.14 to 22/7 to 333 over 106, these numbers as decimals are getting closer and closer to pi. So eventually, if I took this and made it pi, what's the error going to be if that number becomes pi? 0. So then if I use that symbol instead, that number, I get an exact answer, and I don't have any error in my work. Does that make sense? And that's going to be something that we're going to talk about throughout this course. Your geometry teacher will talk about this. You have me for geometry at some point. We will talk about this. Okay, but I want to make sure you understand. We'll talk about the times and when it's appropriate and inappropriate to use rounded values. Okay? If I'm doing a story problem and I want to know the volume of something, I want to know, maybe I'm working on sending people to Mars. I want to make sure that I'm using as exact values as possible. I don't want to round values and send something to Mars that, because of my calculations, doesn't get there. Does that make sense? Okay. So just want to make sure that those ideas are discussed and talked about when it's appropriate to use exact values and when it's not appropriate. But using rounded numbers creates error in your final answers. Okay, so we want to minimize that. The back of that sheet, guys, I don't want to do the rest of those, but the back of that sheet, if you want to attack those on your own, I think that's a good idea. I would stay away from question number 6. Starts talking about radioactive decay and that kind of stuff. You don't need to worry about that right now. You can do it, okay, but you don't need to. The answers are upside down in the bottom right-hand corner of that if you want more practice, okay? Do you guys have any questions over the homework, over 2.10? Yes, Lindsay. Iceberg lettuce is grown and shipped to stores for about 20 cents a head. Consumers purchase it for 46 cents a head. Okay, so find the percent increase. Okay, so this one, so lettuce is shipped for 20 cents and then priced at 46 cents. That's what it says, right? Okay. They want to know what the percent increase. Okay. So remember, percent increase or percent change is equal to new divided by old, right? Okay. So what is your new value? 46 minus then your original, which would be 20 over 20, right? Now think about it when I multiply this by 100 then eventually. If it started off as 20 cents, doubling it would give me 40 cents, right? So you're going to see that this is more than a doubling process. So let's look at our answer here and think if I take 46 minus 20, that's 26, right? Okay, so 26 then divided by 20 as a decimal is 1.3. And if I multiply that by my 100%, it gives me 130%. Does that make sense? Okay. When you double something, that's a 100% increase. So when I see it that goes above a doubling amount, it's more than 100% increase. Does that make sense? And 30% increase. Or actually, sorry. Yeah, sorry, 130% increase. What did you have typed in? That's okay. Don't worry about it. Tomorrow, like I said, guys, we're going to go over that quiz we took last Friday. I want to make sure that we attack that and make sure we are understanding of what is going to be expected of us on Thursday's test, because that's going to be that quiz is the foundation of that test, and we're going to add some of this stuff with percents and percent change on that as well. That's all I've got for you today.